In this presentation, I am going to explain DC motor drives, different types of DC motor drives, and its speed, torque, characteristics, etc. DC motor drives. DC motors can be classified into separately excited DC motor, shunt motor, series motor, and compound motor. Now, in separately excited motor, the armature and the fields are excited by independent voltage source. The armature and the fields, they are excited by separate DC source. In DC shunt motor, the field winding is connected in parallel with the armature, both of which are supplied from the same source. Therefore, in shunt motor, both the field and armatures are connected to the same source. And the third one is the series motor. In series motor, the armature and the fields are connected in series and they are supplied from the same source. Therefore, in series motor, both armature and the field, they are connected in series and they are supplied from the same source. And the fourth one is called compound motor. In compound motor, there will be series as well as shunt winding. Therefore, both series and shunt fields are present. The performance of the motor is determined by the relative strength of the series and shunt field. Therefore, this is representing a compound motor in which there is a shunt winding is there as well as series field winding is there. Both are supplied from the same source. Continuing DC motor drives. DC drives are widely used in applications requiring adjustable speed, good speed regulation, frequent starting, braking, and speed reversals. These type of application, DC drives are widely used. And based on that one, the applications are, it can be used in rolling mills, paper mills, hoist, machine tools, traction purpose, and printing press, textile mills, cranes, etc. A wide application is the DC motor drives. And the advantages of DC motors are, of course, low cost as well as reliability is also very high, and the control technique is very simple. These are the advantages of DC motor drives. In a separately excited DC motor, it is possible to control both armature voltage and the field current so as to control the speed over a wide range of in the smooth manner. Therefore, that is possible in the case of separately excited. We can control the armature voltage. Similarly, the field current independently you can control both. Therefore, the speeds ranging from 0 to base speed may be obtained at constant torque by armature voltage control. If you control the armature voltage, you can get a speed below the base speed. And if you want to have a speed above the base speed means the speed corresponding to the rated voltage. That's called the base speed. Now, if you want to control the motor above the base speed, the speed corresponding to the rated voltage, that is above that one, it is there possible at constant power output by weakening the flux. By weakening the flux, it is possible. Or above the base speed, we are using the field control, and below the base speed, you are using armature voltage control. Coming to the steady state equivalent circuit and the speed torque characteristics of the DC motor. The steady state equivalent circuit is like this one. It is the supply voltage capital V, and the back EMF is represented by capital E, and the armature terminals A1 and A2, and the armature resistance RA, that is represented externally. That is, RA represents the resistance of the armature winding that is connected externally. So this is the equivalent circuit, and the corresponding equations are, as you know, that back EMF, induced voltage, back EMF is equal to 5 Zn divided by 60 into P by A, where phi is the flux per pole, that is in Weber. Z is the number of conductors, number of armature conductors, that is Z. N is the RPM, rotation per minute, and P is the number of poles, that is A is the number of parallel path. If it is a lap winding, A is same as the P, and if it is a wave winding, number of parallel path is equal to 2. Therefore, this is the equation for the induced EMF or the back EMF, of course, the back EMF in the case of a DC motor, which is equal to 5 ZN divided by 60 into P by A. Substituting for N, that is in terms of omega, substituting that one, we will be getting it is equal to 60 into omega M divided by 2 pi into P by A, or that is equal to Pz divided by 2 pi A into 5 into omega M. This is a constant for a particular machine. Number of poles is constant, number of conductors is constant, number of parallel path is constant. Therefore, as far as a machine is concerned, Pz divided by 2 pi A, that is a constant. That is called the motor constant, that into flux per pole into omega M. Therefore, the back EMF is equal to this constant, that is represented as Ke into phi into omega M, where Ke is equal to motor constant, which is equal to Pz divided by 2 pi A. Now coming to the equation of this one, the DC input voltage is equal to the back EMF, which is opposing the supply voltage, plus IARA, the drop across the armature resistance, or IARA plus back EMF is given by Ke into phi into omega M. Or from this equation, you can calculate that omega M equal to V divided by Ke into phi minus IARA divided by Ke into phi. But already you know the basic equation for the torque and armature current and flux. T is equal to Ke into phi into Ia. That's the torque produced by the motor equal to a constant, the Ke into phi into Ia. Or from that equation you can calculate what is the armature current in terms of torque, which is equal to torque divided by Ke into phi. Substituting this armature current in this equation, the basic equation you will be getting omega M equal to V by Ke into phi minus Ra into T divided by Ke into phi whole square. Therefore, this is the equation or relation between the speed omega M as well as torque. Omega M equal to V by Ke into phi minus Ra divided by Ke into phi whole square into the torque T. Where already I told P is the number of poles, Z is the number of conductors, A is the number of parallel path, A equal to 2 for wave winding, it equal to P for a lap winding, and omega M is the angular velocity in radians per second. Now let us see the speed torque characteristics of different types of motors: DC motors, shunt, separately excited, series motors. And the generalized equation for the speed omega M, angular velocity omega M equal to V by Ke into phi minus Ra divided by Ke into phi all square into torque T, where Ke equal to, we have already derived the equation for this motor constant Ke, Pz divided by 2 pi A. For separately excited DC motor or for shunt motor, flux is a constant. That is, for separately excited motor and shunt motor, whether here or here, the flux is equal to a constant. Once flux is equal to constant, the constant Ke into phi will be another constant, because flux is a constant. Therefore, Ke into phi is another constant, that is represented as another capital K. K into phi product is K. Therefore, this equation, the generalized equation for the speed and torque, that will become omega M for a separately excited motor and a shunt motor. Omega M is equal to V by K minus Ra by K square into torque. Therefore, omega M equal to V by K minus Ra by K square into torque. This is the equation for a shunt as well as separately excited DC motor. Now coming to the series motor, the flux is, that's not a constant, that's a function of the armature current, and that constant we call it as Kf. It's a field constant Kf. Therefore, flux equal to Kf into Ia, or you can say that one torque is equal to Ke into phi into Ia, or that is represented as Ke into Kf into Ia square. Therefore, the torque is for a series motor, torque is this equation, or from this equation you can find out what is Ia. Ia is equal to root of T divided by Ke into Kf. This is the equation for the armature current in the case of a series motor. Now coming to the basic equation for back EMF, already it is equal to Ke into phi into omega M, or phi is equal to Kf into Ia, or Ke into Kf into Ia into omega m. Or omega m is given by, that is, you are replacing the phi by Ke into Ia. Therefore, V by Ke into Kf into Ia, or phi equal to Kf into Ia. Therefore, V divided by Ke into Kf into Ia minus Ra divided by K into Kf into Ia whole square into tau. Now here, substituting for Ia from this equation, we will be getting V divided by K into Kf, the square root of T divided by K into Kf minus Ra divided by Ke Kf into root of torque divided by K into Kf all square, that into torque. Or in that equation, we will be getting the, for a series motor, speed omega m, angular velocity omega m is given by V divided by root of Ke into Kf into 1 by root of T minus Ra divided by Ke into Kf. Or omega m is inversely proportional to the square root of the torque in this case. Series motor. Therefore, in a series motor, omega m is given by V by root of Kf into 1 by root T minus Ra divided by K into Kf. Where in this case, the Ra is, it is the total resistance of armature and the series field winding resistance. The sum of that one is represented as this Ra. Now, if you plot the T versus omega m for a shunt motor, you can see that one omega m equal to V by K minus Ra by K square divided by T. Therefore, as torque increases, this component is increasing, slightly increasing, because Ra value is very small. This component is slightly increasing as torque increases. Because of that one, the omega m is slightly reducing, V by K minus that one. That is why in shunt motor, as torque increases, speed omega m is slightly reducing. This is for a shunt and separately excited motor. But for a series motor, the omega m is inversely proportional to the square root of the torque. That is why it is something like this one. You are getting an inverse characteristics. As torque increases, omega m is reducing. This is for a series motor and this is for a shunt motor. And for a compound motor that we'll be seeing later, that consists both series winding as well as shunt winding. It will be in between. A characteristic will be in between of shunt motor and series motor. Therefore, this is the torque speed characteristics of different types of DC motors. Continuing speed torque characteristics of shunt separately excited series motors. In shunt and separately excited motor, we have found omega m equal to V by K minus Ra by K square into torque, where V is the applied voltage, K is a constant, which is equal to Ke into phi, and Ra by K square into the torque. That is why this is the characteristics of torque versus omega m for a shunt motor. And for a series motor, omega m is given by V by root of K into Kf into 1 by root of T minus Ra by K into Kf. Therefore, as torque is increasing, omega m is reducing, but it is inversely proportional to the square root of the torque. That is, there's an inverse characteristics for a series motor. And the shunt motor is this one, and compound motor will be in between this one. So for a series motor, speed is almost inversely proportional to the square root of the torque. Therefore, a high torque is obtained at low value, at low speed. Therefore, at very as low speed, you are getting a large low speed. Is obtained at a low speed, and at a low torque is obtained at a high speed. Inverse characteristics. Series motors are therefore used where large starting torque is required, and as in the case of cranes or traction purpose or hoist, where you need a large starting torque, that is in traction purpose or cranes or hoist, there we use series motor. Therefore, a series motor starting torque is very high compared to shunt motors. Now let us see the speed control of DC motor drives. Therefore, in speed control of DC motors can be classified of the can be controlled by any of the following methods. Can be either by controlling the armature voltage, that's called armature control, voltage control. Second, field flux control, and third is armature resistance control. Now let us see first one, armature voltage control. Now, as you know that relation for omega m and torque for a separately excited motor and shunt motor, V by K minus Ra by K square into torque. And in this case, you see that one, if you vary the armature voltage, you cannot bring the armature voltage more than the rated voltage. That is why this method of speed control is used for speed less than the base speed. Therefore, this is the speed corresponding to the, so this is the plot corresponding to the rated voltage. That is rated voltage is this one. You can reduce the voltage, and if you reduce this voltage, what happens is that omega m in this one, as you reduce the voltage V by K, that value reduces. That is why this y-intercept is reducing. That is V by K is reducing. And here this represents the torque versus omega m for different values of the voltage. This is the corresponding to the rated voltage, less than rated voltage, again less than, or here we can say that V2 is less than V1, which is less than V rated, or the rated voltage. This is called armature voltage control for a separately excited or shunt motor. And in the here series motor, similarly, it can be used for the speed control less than the base speed. Therefore, that is neutral. This corresponding to the base speed. Therefore, as you reduce this voltage, you can see that one that is shifting towards this side, and here the speed is getting reduced. Therefore, that relation corresponding omega m and t equal to V by root of Ke into Kf into 1 by root of T minus Ra by Ke into Kf. This is the relation corresponding to the series motor, and this is the relation corresponding to the shunt motor. For the armature voltage control, you are changing the voltage V. Now, in armature, voltage control is preferred because of the high efficiency, good transient response, and good speed regulations. And armature voltage control can provide speed control below the rated speed. Below the base speed, this can be used, armature voltage control technique. Second method of speed control of DC motor is the field flux control. By controlling the field flux, you can control the speed of the motor. Therefore, this is representing for a separately excited motor, a shunt motor, and this is representing for a series motor. Therefore, the field flux control can provide the speed control above the rated speed. That is, this is corresponding to the rated voltage. The speed corresponding to, right, that's called the base speed. Above that speed, it can be used. Therefore, this is corresponding to the rated speed corresponding to the rated voltage, or by okay, so if corresponding to the rated flux also, we can say that corresponding to rated flux that is running at rated speed. Therefore, if you reduce the flux here, that is, this flux is phi1 is less than phi, and again phi2 is less than phi1. If you reduce the flux here, field is weakening and the speed is increasing. That is for a so the field flux is reducing. As the field flux reduces, the speed is increasing. This is for a shunt motor. That is the field flux control above the base speed. Similarly, for series motor also, this is the corresponding to the rated flux. Corresponding to rated flux, this is the characteristics. Omega m is torque for a series motor. Now, if you reduce the flux like phi1, which is less than phi, again phi2, which is less than phi1, in that case, you can see that one, the speed is going above the base speed. For the speed control above the base speed, you can use field flux control, and this is the speed torque characteristics for a separately shunt and series, separately excited shunt and shunt motors, and this is for a series motor. Next method is called armature resistance control. In armature resistance control, you are changing the armature resistance. That is, for example, in this case, omega m equal to V by K minus Ra by K square into T. For the same voltage, what you are changing is this Ra you are changing. If you change this Ra, this drop is changing. As this drop changes, for example, if you, this is a very small value of Ra. If you are increasing Ra, that is dropping in a very faster rate. Again, if you increase Ra, again it is getting a faster rate. For as Ra increases, the characteristic is shifting towards like this one, and this is corresponding to for a shunt or separately excited motor, and this is for a series motor. Again, if Ra increases, the curve is shifting towards left side, and the corresponding equation, as you know, V by root of K into Kf into 1 by root of T minus Ra by K into Kf. This is speed torque characteristics as the Ra or as the armature resistance is increasing. Well, you take the armature resistance in this case for a series motor, you have to, it is the you have to take total armature resistance of the field resistance also into consideration. Therefore, in the scheme, there is a more wastage of power. That is a disadvantage of the armature resistance control. You can change the speed of the motor, but there is a wastage of the power in the armature resistance. Now let us see constant torque and constant power operation of a DC motor. Maximum torque and the maximum power of a DC motor drive operating with a armature voltage control with full field below the base speed, and the flux control at the rated armature voltage and above the base speed. Therefore, armature voltage control is used less than below the base speed, and the field control is used for above the base speed. Therefore, this is the base speed. Less than the base speed, we are using armature voltage control, and more than the base speed, we are using field flux control. For in the case of armature voltage control, in armature voltage control, at full field flux, you are applying the full field flux and you are controlling the armature flux. Hence, the maximum torque that the machine can produce, that is because torque is proportional to Ia. Therefore, the maximum torque that can be produced is a constant. Therefore, if you are allowing the maximum armature current, torque is equal to constant. In that case, this is case maximum torque is a constant. Maximum torque that can be obtained from the motor is a constant in armature voltage control. But the power, we can say that power is the product of torque and omega m. Therefore, as omega m increases, because a constant torque is there, the power is increasing linearly. Therefore, this is the power variation, maximum power variation during the armature voltage control. And this is the maximum torque variation. That's a constant torque. Therefore, this is a constant torque operation below the base speed. Therefore, because E and V are constant, hence maximum power developed by the motor has constant value corresponding to maximum load. Therefore, the maximum power developed by the motor, that is during the field control. This is what I explained for the base. But during the field control, that is if the above the base speed, that is working in the this region, that is constant power mode. And in that case, because E and V are constant, and the maximum power developed by the motor has a constant value corresponding to the maximum load. This is constant value. Therefore, this operation is corresponding to the field flux control, and this operation is corresponding to armature voltage control. This is the base speed. Above base speed, you can have a constant power, and below the base speed, you can have a constant maximum torque. Therefore, this is the torque and maximum power plot. Continuing constant torque and constant power operation of DC motor. Below the base speed, armature voltage control method is used. That is, less than the base speed, armature voltage control method is used. And during this speed range, maximum torque is constant. And maximum power increases linearly. The maximum power output available is increasing linearly, less than base speed. That's called constant torque region. This is what we call it as a constant torque region. And above the base speed, above this base speed, flux control we are using. Flux control method is used. And during this speed range, the maximum allowable power is constant. And the maximum torque is inversely reduces. Therefore, torque is inversely reduces as the omega, because P into omega equal to torque. Therefore, here, T into omega equal to power, or torque equal to P divided by omega. Therefore, it is inversely reducing here for the power, that is a constant, and the maximum torque inversely reduces for constant power region or the field weakening mode. This is the field weakening mode in which the maximum torque available is reducing linearly. I mean, it's inversely, of course, reducing inversely, but the power is equal to constant. Therefore, this is a constant torque region, and this is a constant power region operation of a DC motor. Coming to a problem, a 200 volt, 10.5 amperes, 2000 RPM shunt motor has a maximum, has armature and field resistance of 0.5 ohms and 400 ohms respectively. It drives a load whose torque is a constant at rated motor torque. Calculate motor speed if source voltage is dropped to 175 volts. Coming to the solution, if flux at 220 volt is 5.1, and then flux at 175 volt, because flux is proportional to the voltage. Flux at 175 volt, that 5.2 is equal to 175 divided by 200 into 5.1, or it's equal to 0.87551. This is the relation 5.2 equal to 0.87551. Since the load torque is constant. The problem, load torque is constant. Load torque is constant means armature current is constant. Or load torque is, again, we can say that load torque is constant. Okay, load torque is constant. Torque is equal to product of armature current and the flux, because flux is also varying. Therefore, as phi Ia1 into phi 1 equal to Ia2 into phi 2. Or you can say that one Ia2 equal to phi 1 divided by phi 2 into Ia1. Or substituting that one, we'll be getting it is equal to 11.4 amperes. That is the current, armature current corresponding to the reduced voltage 175 volt is equal to this one, 11.4 amperes. And the corresponding back EMF, for example, the first case, the back EMF is given by the voltage V1 minus Ia1 into Ra, or 200 minus 10.5 into 0.5, 195 volt. The second case, reduced speed 175, sorry, reduced voltage 175 volts, it is equal to V2 minus Ia2 into Ra, 175 minus 11.4 into 0.5, it is equal to 189.3 volt. Continuing the problem, therefore, as you know that one, back EMF is proportional to phi into N, or therefore E1 by E2 equal to phi 1 by phi 2 into N1 by N2. Substituting this equation, you can find out what is the speed N2 corresponding to the second case, that is second case of 175 volt. It is equal to E2 by E1 into E2 by E1 into phi 1 by phi 2 into N1. Substituting that one, you will be getting it is equal to 1984.5 RPM.